import. Slicer is importing. Here I will have the patient's name, which I anonymized for now, but of course you can use it with your patient however you like. And we see here the different series importing with the different sequences. So this patient is scanned actually, so the actual slices will have the best resolution, so we will choose them to do the calculation. So one new patient, so many new instances, etc. Okay, now I will click on this one and load it inside my viewer. Here we go, so it's imported, and we see that this patient here has lithiasis on the right side. So scrolling through it, there we go. I will now press Ctrl and scroll to enlarge it a bit. So this is what we're interested in calculating. Okay, what we need to do is use a so-called segmentation, which is a mask of this hyper dense nodule or calculus, and we will do it by thresholding according to the Hounsfield units. So first we make a mask or a segmentation, clicking the segmentation module, selecting a segmentation. We need to create a new one because we didn't have one. We will add one. Here we go, and we will call it lithiasis. You can call it whatever you like, but this sounds the most reasonable name for now. Now that I created it, I will edit it. So I will use the segment editor. I have the lithiasis mask. I will edit it on this volume. Of course, when you load in other slices or imaging series, you can change it here. And I will use the threshold to use my Hounsfield units. So when I see here, I see that I have all fatty tissue, everything included. But if I change my range from about 100 Hounsfield units, I see that the lithiasis is quite well included. Of course, I also have the vertebral column, which is not a problem because I will cut it out later. I will apply the mask like this. So now it's saved here, and I will edit it in 3D. So I will click on, for this mask, show 3D, which will calculate the 3D volume and put it here. I don't see it, but that's because scans are often offsetted from the origin, which is in center here, because that's just how the machines work. And we see that the volume that we selected is here. So everything which is bony is still included. And here we see what we are most interested in. You see, you can turn it however you like. What I will do now is use the scissor tools to edit this 3D volume. So I will just click scissors. I will choose to erase everything outside of what I indicate and do it freeform, so that I can just pull a small circle around what I need, like that. 3D slicer will cut it. We see that there's part of what's behind the patient, his bed that was scanned with him, is also there. We will again, so we are interested in this, almost turned on the wrong region. So now I have the volume that we are interested in. Okay. Now the only thing that remains is checking if we're right with what we selected. So here we see the volume is okay. When we go through the patient, we see going a bit too fast now. You see the calculus here. Okay, so that's kind of the best that it gets considering the slice thickness, but it gives a very good approximation of the exact volume. As an ellipsoid or for other shapes of renal calculi, it's very easy to use. Now we will use the last module, which will give the statistics of the segmentation of this mask. So I will click the module segment statistics. I will choose the volume that I'm interested in. I will create a new table. Okay, I will click apply. And here we see that our mask, which is just this volume in 3D, has a volume of 630 square millimeters. The Hounsfield units, the minimum is set on 100, which was our lower value. The upper one of what remains here is not 1380 like what was the maximal Hounsfield unit in this scan, but is lower to 1295. And we see though we can also have the surface area and other characteristics that might be useful.